Hi, I'm Steve Kinney, Director of Training, Compliance, and Technical Solutions for Smart Vision Lights. Welcome to our latest webinar, Imaging the Unseen. In today's webinar, we're going to talk not only about what the camera sees compared to your eyes, but we're going to talk about using non-visible wavelengths of light, either UV or shortwave infrared, which the camera can see and your eyes cannot. During today's webinar, please enter any questions you have in the comments box. We will collect the questions, and at the end of the segment, we will answer those. To begin with, machine vision is one of the most powerful technologies for manufacturing today. It's been in a prolific rise since the late 90s, and machine vision is becoming very common. Yet, most cameras and general machine vision focus on imaging in the visible spectrum of light, the spectrum which we can see with our eyes. This is partially due to the equipment that was available through the history here and the development, but also because quality inspectors and other machine vision professionals are more comfortable implementing inspections that match what they can see with their eyes. But developments in UV and shortwave infrared components in both cameras and lighting have dropped the cost of imaging in the non-visible spectrum and also made components that are much more readily available. If you're well versed and understand these areas, then using the additional areas of imaging offered by UV or SWIR can do things that we cannot do in the visible spectrum, and many of these are useful for typical machine vision tasks. Today, we're going to talk through those advancements, what it means in the equipment, and then some practical examples of how you can use this to your advantage in machine vision inspections. So what do we mean by non-visible imaging? Well, to begin with, human vision generally covers wavelengths of light from 400 nanometers to about 700 nanometers in a general sense. The actual response of any individual human varies, much like hearing, and there is no fixed cutoff. But in general, people see from a deep blue violet at 400 nanometers to a deep red at 650 to 700 nanometers. It's notable, though, that light is a continuous spectrum, part of the RF spectrum, just with more energy, and that wavelength energy increases and wavelengths gets shorter as we move through the infrared into visible imaging and through the visible into the ultraviolet and shorter wavelengths. So when we say ultraviolet, it's ultraviolet because it's a shorter wavelength than human visible blue-violet at 400 nanometers. And when we say short-wave infrared, it's infrared and it's short-wave infrared because it's wavelengths just longer than what we perceive as human red. Short-wave infrared refers to those closest to the human spectrum. It is notable that the infrared spectrum extends into medium and long-wave infrared, which we're not going to talk about today, and includes other properties which are not kind of like visible light. When we talk about UV and shortwave infrared, they're still non-visible spectrums, but the behavior is much like light, and as you'll see, we can image in a very standard way using these spectrums. It's also notable, we're talking about light, which is a very short wavelength, and just as a point of reference, the wavelength of visible light, to make a generalization, is about 1/100th the diameter of a human hair. So we're talking very small numbers here. So what do we need to image in the non-visible spectrum? On your screen, you currently see a UV imaging system. And the first thing I want you to notice is, if I weren't talking about it and we weren't labeling these components, it would look the same to you as a visible imaging system. In fact, this is a standard Matrox Iris GTR smart camera. It is not necessarily a UV specific or a tuned UV camera. It does still have response below 400 nanometers. Though there may be some attenuation, it will capture the UV light at 365 or 395 nanometers. Similarly, this is an Edmund Optics Tech Spec lens. It is also important to point out that you should be seeking lenses that are specifically designed for machine vision. This is because photographic and security type lenses are aimed at making visible images and outdoors. Many of these have UV blocking coatings which are necessary for security cameras and other photographic applications, but obviously will then also block the UV light when you're trying to use them for machine vision and non-visible imaging. So be sure that you check your lens, that it's a machine vision quality one with no filters, and that it has accurate response, or go ahead and invest the money and buy a UV specific quality lens. Additionally, you see there is lighting. As for any imaging application, we need cameras, optics, and lighting. But again, you'll notice this is a Smart Vision Lights RMX 140 ring light. And while we've loaded it with special LEDs to transmit light in the UV range, it is in fact a standard product in a standard form factor. And to the user, you really wouldn't notice anything different about it other than the fact that you cannot see the light coming from it where the camera can. Similarly, we see a SWIR imaging system on your screen now, and you'll notice it doesn't look that different. In this case, we do have to use a SWIR specific camera, and this is a Teledyne DALSA with a Sony IMX 990 hybrid SWIR sensor in it. And this is because the shortwave infrared does not register on silicon. The near infrared at 850 or 950 nanometers will register on some visible sensors, but largely it takes a specialized sensor to capture the shortwave infrared spectrum. So in this case, we do need a special camera, and shortwave infrared cameras are typically very expensive, especially in history. They have been what we call InGaAs, or indium gallium arsenide, and an InGaAs sensor is a different manufacturing process than a silicon sensor, and that has made them very expensive. But two recent breakthroughs have brought the cost of SWIR imaging cameras down. One being the Sony IMX 990 hybrid sensor that I previously mentioned. This sensor has a InGaAs sensor and pixel readout structure, but the back end of the shift registers and actually reading out or clocking out of the image is CMOS, and they are copper on copper bump bonded through a special technology developed by Sony to make a lower cost sensor. Similarly, the other technology which has been helping us is quantum dot technologies like those offered by SWIR Vision Systems and others. Quantum dot sensors also lower the cost and work in a slightly different way. They are essentially a CMOS sensor and readout structure, but they have a colloidal quantum dot slurry put over the top of the sensor. So then the shortwave infrared light reacts with the quantum dots in that slurry, which give off electrons, which are then captured in the well. Both of these technologies are competing with each other and helping lower the price of SWIR imaging in the market. Lastly, we have to mention the SWIR optics. And the same as kind of the UV optics, sometimes visible optics work, but because of the long wavelength, even more so than in the ultraviolet range, you have special considerations. Thus, in SWIR imaging systems, almost always you should buy a SWIR intended lens that is specially designed and compensated for the longer SWIR wavelengths. So the real key here is to understand what we can do with SWIR lighting and how to apply this in order to design your similar machine vision system and take advantage of this. So we've talked about the non-visible imaging system and how the components of the system itself are familiar and look like your visible imaging system, but just specialized for the spectrum. Let's take a minute though and talk about lighting in the spectrum, since it is crucial to the imaging system. It is notable, while light is a continuous spectrum, and we're talking about everything from longer wavelengths in SWIR to the UV, LEDs are available at only specific points in here, so we must choose an operating point that we're going to work at. The most common wavelengths in the UV for the machine vision market are 365 and 395 nanometers. This gives you a soft UV and a little bit deeper UV. It is also notable you can image down to about 250 nanometers or below, but as we go shorter in wavelength and into those areas, the energy per photon is increasing, and things like eye hazards and other interactions are becoming undesirable. And in fact, by 250 nanometers, a UV photon has so much energy it can actually damage the silicon imagers or the articles being imaged. This is done in semiconductor manufacturing, but for practical machine vision and today, we're going to talk about just the near UV and 365 and 395 nanometers. Similarly, if we look at the SWIR spectrum, you will notice that we have many more data points, but that's because we're talking about the long end of the spectrum instead of talking about the 50 or 60 nanometers just shorter than blue light. We're now going to talk about several hundred nanometers longer than red light. And because of this longer spectrum, then there, of course, are more data points of LEDs available. And you can see these, I'm not going to talk all the way through, but we have good LED choices for SWIR imaging from 850 nanometers in the near infrared all the way out to 1650 nanometers in the SWIR range. So let's talk about some practical uses now about non-visible imaging. Well, for one thing, we can get additional information, just like we can use color as a discriminator and use color to highlight or attenuate things we see in the visible range. As we get outside the visible range, the light still behaves and interacts with the surfaces, but differently than the visible. In some cases, there may not be any difference, but in other cases, just outside the visible range, the product or object under inspection may absorb or reflect a lot of light, even though that's not what's happening in the visible. So we can use this information to see what can't be seen in the visible spectrum in many cases. And that includes detecting water or moisture content, which is very important in many machine vision applications. It means we can see through opaque plastic containers, and we can check fluid levels behind them as we're filling them, or check for components that are already in some kind of sealed enclosure, make sure they are correct in a final check before the product is passed on for packaging. It also means we can see inside opaque packaging, and we can also see with UV fluorescence of adhesives and greases. And these principles are all very important in many practical inspections that we need to implement in our machine vision lines today. So let's begin to look at some of these practical examples. One of the most common here is using SWIR imaging to detect bruises on fruit. And in this example you see on your screen now, you see a color image of a peach. And the color image in fruit inspections and stuff, often there's dual imaging going on because we do need a color image, and in this case on the peach, because they need to see that the flesh of the peach is turning a nice rich orange color, orangish yellow if you want. They need to see the dark red and orange striations on the yellow flesh and other things to be sure the peach is ripe and looks good for the consumer. So they will take a visible image. But what's equally important is the quality of that peach or any fruit here, and whether it's been damaged or bruised. And as you can see in the SWIR image, we've used 1450 nanometer, something in the middle of the SWIR range here. And with that imaging, you can see a monochrome image, and you can easily see the bruises standing out. When you have bruised and damaged cells, the boundaries break down, and those areas begin to absorb more water out of the flesh of the fruit. And it's in fact that higher water content which is turning dark in the SWIR range, which then makes it stand out in these images. It's also noted that we're showing you the basic effects in this, but that if you need more contrast than this, or if you're working on a specific product, it's very common to use narrowband notch filters to isolate the best frequencies for the product you're looking at and to maybe block some stray light and other things which may dilute this process. It's also notable, I used a peach, but that this process we're talking about, finding bruises on fruit, works on many types of fruits and vegetables for the reason I said about cell damage. And in fact, on this slide, you can now see side by side a good and a bad bruised strawberry at the same 1450 nanometers. So peaches, strawberries is very common on apples, grapes, blueberries, other types of fruit, to use this kind of imaging to detect bruises and find the quality. So let's carry this example forward and see how it applies to medical imaging. Though the objects under inspection are different, moisture contamination in sterile medical products is in fact a problem during their production. In this example, you see very simply a packaged Band-Aid. But Band-Aids must be dry, they have gauze pads, they're in a paper package as we're all familiar with. And in the visible image, you can see what the consumer needs to see. And again, they may image in the visible before they do the SWIR in order to see that the bandage is properly packaged. But again, if it's contacted any kind of moisture along the way or absorbed it, it is definitely a problem for them. So you can see in the middle image is a SWIR 1550 nanometer image of a good bandage. And now we're using a backlight to backlight through the packaging and see what is inside. And while it's hard to detect everything that's going on there, you see that the good bandage image is uniform. We can see the bandage is uniform. We can see a little bit of overlap in the packaging and a stripe in the middle of the gauze pad, but it's clear to tell that this is all very well behaved and there's no real contamination here. If we looked at the same image but on the bad or contaminated sample there, it's easy to see that that gauze pad has now contacted moisture somewhere and that is wicking in from the sides, and that those areas turn dark. There's no longer a nice uniform pattern. And again, with standard machine vision tools, we can fairly easily detect this kind of contamination. In fact, I want to point out something to you here. If you look at the bad or contaminated image, we obviously had to make these examples for our own webinar here, and we did so very manually. And if you'll notice, the other thing that the SWIR can help you see here is on the left-hand side of the bandage, you'll notice you can see it's brighter between the edge of the paper packaging and the top of the Band-Aid. And that's because we actually peeled that packaging open, contaminated the Band-Aid, put it back in there and sealed it. But the area where we had to peel to get in at all at the top is now very light because the adhesive has been broke, and even though it may stick back together a little bit, there's trapped air and other things. And as an added benefit, we can actually do the sealing inspection besides looking for the contamination here. But water moisture is not the only kind of contamination or problem we can have in our medical inspections. In this example, we see a package of acetaminophen, and it's in one of these typical kind of plasticized paper packages where you tear and open. In other cases, you might actually have laminated plastic or even the kind of pseudo foil line that are still out there. If it's true foil package, light won't penetrate it, but even the pseudo foils, often SWIR light will pass through it. And this is important. Again, they're going to use a visual image, make sure the coloring's right, make sure all their ingredients and other things by law are correctly on there in a way consumer can get the information they need. But after they're done with this, they do need to check and make sure that the right dosage is in there, that there's 2 pills and not just 1, none, or even 3 or 4 pills in there. And they need to do some verification before that package is put in a larger package or box and shipped off for the consumer. So on the SWIR 1550 nanometer backlight, you can see we've placed the package. And similar here, the image that's a good packet, you can plainly see there are 2 pills contained inside. On the one we're showing as a bad packet or empty packet, as we've labeled it here, the pills have been removed, and you can see through the packaging and tell that there in fact is no contents inside this, and that it would be immediately rejected by the machine vision system. So it can help. SWIR imaging can help us see within packaging and make final quality analysis that wouldn't be possible otherwise. So let's move to the next example and carry this kind of presence-absence detection forward, but let's look back again at a food product. In this case, we have a K-cup, which most of us are familiar. So if we look at the visible image, then we can see the foil on top, and we can check and see that it's not breached and so forth. But we can only see the white physical plastic of the sidewall. We can't really tell what's going on inside. So if we now light these with a SWIR 1550 nanometer backlight, as you see in the 3 images contained in the label there, and we look at a good K-cup, there is both coffee in the top and a filter in the bottom of the K-cup, and both things must be present in order for it to work properly. And we can tell there's coffee in the top because we can see how dark the contrast is, and the coffee is actually blocking the SWIR light from coming through the packaging. And we can see the lighter portion in the bottom of the K-cup there, which is the filter itself, and even though it's blocking more than the sidewall, it's still passing more light than the coffee. So we can see the dark and the light that make the coffee in the filter. If we look at the first bad K-cup image, then there, in this case, there is a filter present, but there's no coffee. And we can tell this, even though the top is still darker than the bottom, we can see it's a medium contrast. It's not blacked out like when it's full of coffee in the first image, and that there's no coffee attenuating the signal coming at us. But if you look close, we can also see the filter in the bottom, but you'll notice there's actually a white ring at the top of the filter that you can't see in the good image. And that's because the white ring is actually the seal to seal that filter against the bottom and not let coffee around the filter. And in fact, you can use that to your advantage because we see that bright seal in one with no coffee, and in the properly filled one, the coffee actually presses in and around that seal, but not past it, and you shouldn't be able to see it if it's properly filled. And in the last of these 3 SWIR examples we have here, there is neither a coffee or a filter. Somehow this has come through the process. There's an aluminum seal on the top, but in the fill process, it's a blank in both steps, and they've sealed an empty container here, and that, of course, is really bad, and they want to reject that. And we're going to continue forward now and look at the same principle, but now we're going to talk about polyethylene containers, but filling them. But polyethylene packaging is very common in the marketplace now, and they have to still have the same kind of quality controls, even though they can't see through there. In this case, we want to fill the package to the proper level. And if you look at the SWIR images we've captured with the 1550 nanometer backlight, You can see on the one furthest on the left is an empty bottle, and much like the coffee, we can see there's just an even grayscale from the package itself, but there's no dark fluid inside. In the middle image, then we have a filled bottle with approximately 55% of the fill. And in the last example here, there's actually an overfilled. They want to fill this bottle with fluid to a nice level and leave a little air at the top, as we find in our packaging, and then seal it. But in fact, there's been an error in the fill of this one, and it's filled it absolutely to the top, which is equally as bad. And this one's what we're going to call 105% fill, or something greater than the 100% target. So all these conditions can be detected with SWIR imaging through the bottle, or if you have spray bottles or other things, you can make sure they're at the top correct fill level without having to use a physical probe of some sort. There are other non-vision ways to do this. There are capacitive probes that go down there and other things, or even surface detection sensors where they use like a near-infrared beam and bounce it off the surface and kind of measure. With machine vision, we actually can monitor this in an active kind of way and with no contact, but much more accurately than other non-contact methods. In this example, we're going to talk about differentiating materials a little bit. In this case, there are 3 clear fluids, and you can see from the top visible image, you can see a little bit of difference. But if we put these on our 1550 nanometer backlight again, you'll notice that the 3 fluids, which were clear, the acetone, the isopropanol, and peroxide, they actually, some of them turn darker and start becoming opaque. And in fact, the acetone stays perfectly clear, the isopropanol gets the darkest, and the peroxide is somewhere in between. And that's because each of these are acting differently with the SWIR light. And I do want to point out what's making this particular example work for you is that each of these clear fluids has a different water content. And that's why the acetone is the clearest, because there's almost no water in something as hot as acetone, whereas isopropanol has somewhere between 5 and 30% water, and peroxide either has a lower water content or just reacts kind of like the water, but not as strong as the water because being peroxide, and we get something in between there. So if we just have to tell between these 3, it's pretty easy to do this. Carrying on to this next example, we're going to look at this technique, but we're going to start talking about not moisture content in this case, but about applying this to ubiquitous white powders. And though they look similar in the visible range, as you notice in this image, the SVL logo there in the visible range, you can just tell there's 2 white powders in there. In fact, you wouldn't even know there's 2. It just looks like it's filled with white powder and there's no differentiation. However, if we put a 1450 nanometer ring light and illuminate this same logo outline with powders in it, then you'll see very quickly that the 2 powders are not the same. And in fact, one of these is sugar and one of these is salt. And because they interact with the SWIR light differently, the sugar actually it is moisture content again, but within the sugar crystal, there's more moisture. It tends to absorb the SWIR light and turn darker, whereas salt famously repels water, and in the crystalline structure of salt, there is no water present to a very high purity level, and that's why you see in the SWIR that it's still very, very white or reflective. So using 1450 nanometer SWIR light in this case, we can differentiate between 2 similar looking ubiquitous white powders. In this example, we're going to come back to our polyethylene packaging, but we're not going to look in this case for fluid levels. But in this case, we have a container that's used for packaging other parts. So when we look at the visible image in this case, we can see that this is a very opaque, in fact, opaque blue container that you have no chance of seeing through. Yet if we backlight it with a SWIR 1550 nanometer light, you can see through this container, even as thick as it is and as darkly tinted as it is with coloring, we can see easily through this container, and you can not only tell what parts are inside, but you can see that there are 2 of them. In this case, we have a package of Tide brand laundry detergent pods, and these pods are becoming popular for both laundry detergents or dishwasher and dish detergents as well. I think most people are now familiar, and you have a pod with a couple ingredients inside it, 2 sides, and it's a very thin membrane that just dissolves either in the laundry or the dishwasher. So if any water comes in contact, even the littlest of splash or mist on these things, and they're put into these bags, they tend to stick together, and the moment there's any kind of mechanical movement of that bag, they stick and then they tear and rip open, and then once their own liquid is out, it starts melting into the other packages, and you get kind of this lump of material in there. So again, this is really valuable in their production because by just very quickly passing these in front of a SWIR backlight and taking that image, they can see that I have the good Tide package and where to go, or we see something that's not normal or blotchy, we can see lumps or other irregular shapes in there and immediately reject that out of there. So far, we've been looking at SWIR imaging examples, but let's carry these techniques forward and begin to look at the UV and see what we can do in the UV spectrum. In this example, we see 2 bearings. And if we look at the visible image, these 2 bearings side by side look very much the same. In fact, using traditional machine vision tools, it would be difficult to tell the difference between these 2. But many petroleum products fluoresce in the UV. And in fact, if we look at the UV 365 nanometer images, you will see that these 2 bearings are in fact not the same, that you can easily see the one on the right is coated with grease and that it's spread all around the circumference, and that the one on the left has no grease at all. If we look at this next example here, we're going to see an example of adhesive fluorescing, not necessarily grease, and how this is practical. In this example, this is a heating pad, and on this we have a textile mesh kind of backing to give us the flexibility, a little bit of shape as flexibility. We have silicone encapsulated wires where they lay the pair of heating wires down and lay a bead of silicone over it, which must totally encapsulate those wires. And then third, there's a real fine little wire that is woven around to hold the silicone encapsulated wires to the backing. And if we look in the visible range, it's very hard to see any of this. The textile backing is kind of a bone color, and against the light silicone adhesive, it's hard to get any contrast. And with those 2 and the regular grid pattern of the textile, it's very hard to see any of the wires that are holding the silicone down to the textile at all. If we do a monochrome image, it gets a little better because in monochrome we can take advantage, and the textile backing is actually getting a little darker. The white silicone stands out a little more, and in this case, the monochrome is actually helping us get us a little more differentiation than in the color. But it's still not enough to see the binding wires, those little fine wires that are holding the silicone down to the backing. But if you look at the third image, which we captured with a 600 millimeter, 365 nanometer linear light, well, in this case now, the silicone itself actually begins to fluoresce. It is giving, the UV light is exciting the silicone, it's giving off light in a slightly lower spectrum into the blue-green, and it's actually beginning to fluoresce. And because it's lighting, now the textile backing is getting very dark in the UV, the silicone itself is beginning to fluoresce and give off light, and lo and behold, if you look real close or zoom in on that, you can see all the little gaps in the bright silicone, and that's where the binding wire is looping up and around there. So they can actually inspect all three things in the UV, whereas this would be a very difficult inspection in the light, whether it be color or monochrome. So it's very common to use UV to see both silicone and other adhesives like cyanoacrylate or things like that. In this next example, this is actually a practical example from Smart Vision lights ourselves. This is one of our SX30 prox lights, as we call them, spotlight or proximity light. And if we look at this in the visible spectrum, you can see the surface is very shiny, and it's hard to see what is going on there. And in fact, if we just hit it with the UV light and use a visible camera, then you can see the two holes on either side of the connector. Those are actually filled with a epoxy during assembly, where we load the guts in there, spin this thing together, and put some epoxy to fixture everything down and seal those holes. In the top color image, you can actually see it's purplish, not only because it's visible, but because UV lights leak a little bit of visible light. So the purple color is not because you can see the UV or the camera can see it, but largely because there's a little bit of visible light leakage. That's a small percentage of the total UV light that the light makes. In this, you can see the two epoxy holes are in fact glowing, but they're convoluted by the shiny surface and a little bit of light leakage. If we simply use monochrome lighting and take a black and white image, you actually see that the bevel on that ring catches light and lights, but the rest of it turns dark, including the holes. We can't see anything in the monochrome that's useful. But what you can see is if we use the UV light and the UV camera and we put a low pass filter, which only lets the blue and the UV fluorescence through, but blocks all the rest of the visible spectrum, you can actually see that everything else is blocked out, and we only see the two epoxy-filled holes which are fluorescing with the UV light. And that is what we want to see. So with the bandpass filter and UV, we can quickly isolate this down to the two holes that we need to see that are filled and glowing and very uniform. And lastly, for our UV imaging examples here, we want to talk about something that's very common, and that is display inspection for electronics. In this example, we have a cover glass for like a smartphone. And it is very normal on your smartphones. You have an active area in the display and an inactive. So often they coat adhesive around the outside perimeter, glue this thing down, and they need to be sure that they have the adhesive on evenly, and then when it's down, it doesn't infringe into the visible areas that they don't intend it to be. For this display, obviously there's a bezel. They don't need to see the edges like our smartphone, but they don't want any adhesive into the middle. And if we look at a visible image, then we see a piece of glass here, and we don't actually see much of anything that's useful as far as telling where the adhesive is. But if we look at the images with two windows that you see in them, we put two side by side, but what we're showing you here is, again, if I use the UV light and no filter in the one image, we can still see the adhesive, which is fluorescing in the UV, and we tell it's around the perimeter of the window on the right in that image. But in the window that has no adhesive on it, you'll notice the light leakage, again, that was causing the purple haze in the previous example. That light leakage is actually lighting the glass, and we're seeing the glass and some of the surface. And I did this on purpose in this example because in some cases, that glass is clear. You might actually appreciate seeing the outline of the glass and some things, and it might be useful for you. But in other cases, we want as much contrast as possible between that clear glass and the UV adhesive, and that little bit of reflected light, that light pollution off of the visible light onto the glass is a distraction in that, and we don't want to see it. So these two UV images with showing both windows side by side, those are the same two windows in both cases. The only difference is on the second of the UV images, we've used a short pass filter, again, passing only the UV and the fluorescent frequency and cutting off anything in the visible that's a longer wavelength than that. And then you can see that the window itself is almost completely removed out of the image. All we see is the fluorescence from the UV adhesive. So I promised you that this wouldn't be a big commercial, and largely we're talking about the principles here and how they're useful to you. But coming back to my point that these are that both SWIR and UV imaging have become commonplace and are components you generally recognize, this slide is showing you the list of Smart Vision Lights products which are offered in SWIR as standard products. And I'm not going to talk you through this whole list, but you can see we have several types of linear lights, including our specialized nanodrive linear lights for a very fast response. But we also have our miniature lights, we have bricks lights, spotlights, ring lights, proxy lights, and in our SWIR offerings, it even includes washdown versions of these lights. And if you need something you don't see here in SWIR or even UV, then do contact us, because in a non-standard or semi-custom case, we can offer things beyond what you see offered as standard. And if we now compare this to our UV offerings on this slide, you'll see the top part of that list, almost all the same products are offered in UV. In this case, we're not offering the washdowns and a few of the older legacy parts. That's partly due to history. We offered SWIR first, or the product itself, the UV do take special cover glass, so things like the washdown become a special case. And I just want to remind you, these are the same products, just different LED wavelength options in those products. You can see this on the data sheet, and you can choose SWIR or UV in that standard product, the same as you chose white, red, green, or blue. So to wrap this up, I want to talk about, if non-visible is so easy and it's really useful for manufacturing, why hasn't it been adopted more prolific up to this point? And the truth is, this has been around a while, and some do it, but it's not near as common as the visible imaging. And the first thing I want to say about that is that's changing. Machine vision as a whole, as a technology, has been rapidly being accelerated into production, and there's just more and more machine vision happening. And then within that, manufacturers are learning, and non-visible imaging is one of the highest growth areas for both Smart Vision Lights as a lighting manufacturer, but also for the camera companies. So we see that as people are getting wiser and implementing more machine vision, that they're already recognizing that machine vision doesn't have to be visible vision, and they can use these wavelengths. So even though it hasn't been as prolific up to this point, that's rapidly changing. The history in this has also partially been driven for cost. As I've said, a SWIR camera used to be a $20,000 item. Now it's somewhere around half of that, and prices are coming down. Volumes are going up, which even if the technology remains the same, is driving it down. So costs are falling now, which is helping it. The mindset of people putting this and installing these systems has been around visible. Many of those are just learning to think in the non-visible and talk to us and see what else they can do. And to that point, there's been an inability to test or know the results in advance. I can't look at an object and say, well, if I light this with UV or SWIR, it's going to do this, or I'm going to be able to see this or that. Because it's non-visible, you actually can't. You can't always predict what the materials are. You can have some knowledge and know, well, usually greases fluoresce the UV, it doesn't mean that this particular one will, and you basically have to test. But even that is easier than ever now. We have a AE lab here at SVL. You can send us samples in. We will test them. We will show you the different wavelengths, what we can and can't detect, and look at it for you. So it's very easy to either come in our front door and schedule some time to do this, or to mail us a sample and we'll do it virtually for you. But the other option is we have what we call a Smart Color Test Box, or SCB, Smart Color Box. And these have wavelengths. We have one for UV, we have one for SWIR, and they have 6 wavelengths in there where you can press a button and a light comes on at that wavelength. We don't mean these to light with, but you can quickly put it down, do a test with your sample, and see if it's reactive at the various wavelengths, and then determine which lights you may need to move into to do the particular inspection, or if it makes sense to look at SWIR or UV at all. So those test boxes are low cost. If you need them, you can see them on our product or contact your distributor and they can get you one. And it's really powerful to look and tell. The other thing that has prevented this a little bit is eye safety and other things. I mentioned the higher energy of the UV. If you are deploying UV lights, you do need to watch the warnings. You need to, they are not hazardous. Some people avoid them because of the hazard. We have a standard IEC 62471 eye safety ratings on all of our products. You can tell from that the level and what you may need to do to protect. Largely, you just don't want people at very close distances looking directly in the light. If you're taking any effort to shield the light or keep people from directly looking into it, you're probably safe in most cases. We can't tell you definitively. We do offer that you should read the warning, look at the rating. And if you have any questions about safety, contact an EH&S safety officer and they'll do their environmental assessment and make a determination for you. But all these things are changing. This is now a high growth area, and with that, we want to remind you that it's easier than ever to image in the UV and SWIR. The prices for these components are dropping, and that the variety and selection of components in the marketplace is increasing, that the vision systems and the use of the components and the things that you know in the visible are same for the UV and SWIR, and that with just a little bit of considerations that we've gone over in this webinar, you can be deploying these. If you're not sure, ask the experts and get AE support from us or others, and we'll directly help you with the non-visible imaging. As always, whether it's visible, non-visible, UV, SWIR, I want to remind you that it is the light that makes the difference, and you can't get it right without the light. So to bring all this home for you, there are a few things we want you to remember. And that is that SWIR and UV imaging have become easier than ever. If you're familiar with machine vision, that the same kind of components that you're familiar with just some of the considerations we've talked about in this webinar, you can be deploying these systems. If you're not sure, ask the experts, come and get some AE support on non-visible imaging, either by calling us or emailing us. These are the same vision systems, different components or different LEDs in those components, and that this is the same as what you're familiar with in visible imaging, and that the prices and selection of these components in the marketplace are dropping and selection is going up, and that it's very easy to do this. And whether we're talking about the SWIR, the UV, visible imaging, or what it is, I want to remind you, it is light that makes the difference to what the camera sees, and that you can't get it right without the light. And with that, I would like to thank you for watching our webinar today. I hope you have found some useful information in this. I am Steve Kinney, Director of Training, Compliance, and Technical Solutions for Smart Vision Lights. If you have questions, hang on for just a second. There will be a brief pause, and then we will start answering the questions that have been put into the comment section. Thank you. Okay, so moving into our question and answer period now. I have one question that's been put in here that says, can I use UV light for imaging other than making things fluoresce? Okay, so most of our examples in UV we had today were actually fluorescence. The answer to this question applies both to UV and SWIR, by the way. So if we're talking about visible imaging, and in particular color imaging, we teach about color imaging, and the same color will make things brighter. So if I have a blue object and I use blue light, that portion is going to get brighter. And if you use opposite colors, like a red light on a blue object, the object is going to get darker. Those same principles, since UV and SWIR are still light, we just can't see it, those same principles do apply, and sometimes we don't need things to fluoresce or to see through them like in these SWIR examples, and they can be just another color, if you will, and the color may make a difference in your imaging. So you may use UV or SWIR just as an additional factor of color for authentication or inspection. To that point, many textiles, fabrics, if they're black in the visible, they're very dark, hard to inspect, and they look black. But in fact, depending on the fabric, if it's cotton in the SWIR, it still tends to look black. If it's a synthetic fabric, in the SWIR, it tends to reflect a lot of light. So the same black fabric side by side will look quite different in the SWIR, and you can use that again for contrast based on color, and the same for UV. Just because we can't see it, some things will reflect a lot of blue but absorb UV, or vice versa. So just remember, UV and SWIR can extend your color capabilities, not just fluoresce things like we're saying here. We have also another question here. I mentioned the smart color test boxes. We do make both a UV and a SWIR smart color test box. The SWIR has more points in it, and we may eventually have to update it. It may not have the longest wavelengths in it currently, but the SWIR test box has 6 wavelengths in it. The UV one, I believe, only has 3 because we don't do as many, but we do have those available as a tool for you in both UV and SWIR. And then we're going to have one more final question here before we wrap up. And that question, someone has asked, what do I have to do for eye safety in the machine vision system when doing UV or SWIR imaging? So I touched at the end of this a little bit on eye safety in the IEC 62471 eye safety rating that we put on the products. So we as a manufacturer must rate all the products with that eye safety. But there's some important things for you to know. Number one, that testing and that rating that we do is done under specific circumstances to get that. And we're obligated to tell you what the rating for a particular light is using standard terminology and standard levels as defined in IEC 62471. However, that's where it stops for us as a manufacturer. We can't tell you any particular setting or installation is safe or not, because you need to take that information if you're in UV or SWIR and get with an environmental health and safety officer who can take that information, knows how to transpose it, and decide whether your installation is safe. And that's because the eye safety rating is always the worst case. So when we do the eye safety rating, for example, it is as if I held it up in a worst case, looking straight in the light. Worst case is done, that eye safety testing is done at 8 inches, because that's as close as you can get a light to your eye without defocusing, which lowers the risk. And the 8 inches and looking straight in it gives us eye safety rating. And even in the UV, the worst case is we usually get out of the exempt, but they're usually class 1 or 2, which just have general warnings. But light falls with the square of the distance. So in a machine vision system where we're getting away from that 8 inches and we're typically 1.5 to 3 feet, the amount of light that the user is being exposed to is dropping dramatically. And that's why your environmental health and safety officer can make that determination for you. It also makes a difference whether they can in fact look directly into the light, or they're just seeing radiated light directly into it or irradiated light off the surface, those things make a difference as well. So the thing I want to impose on you is there's a higher risk because both of these are non-visible. So when they become bright, there's what we call eye aversion response, and your eye doesn't look away because it's not seeing the light hit, and you will continue to stare. But at the same time, the risk is not so high that you can't easily mitigate it. In case like UV, things like polycarbonates and the other various clear plastics tend to not transmit them, so it may be as simple as encasing it in a plexiglass shield or something. But the thing I again want to impress on you is they're not so unsafe that you have to take dramatic considerations. You just want to make sure you're reading the rating, listening to what the category it says is, and following those exemptions, and making sure that if you have a situation where there's questions, you have the proper EH&S type of advice and how to handle that situation. Okay, with that, I think this wraps up our session. I am Steve Kinney, Director of Training, Compliance, and Technical Solutions for Smart Vision Lights, and we would like to thank you for watching our webinar today, Seeing the Unseen.